Welcome to this explainer. Okay, today we're tackling something absolutely crucial. We are looking beyond basic harness engineering to uncover what's honestly the missing control layer for AI research. Because let's face it, the era of just brute forcing bigger AI models, that's kind of ending. We really need to talk about what comes next. So we've all seen AI models pump out incredibly impressive, fluent answers, right? They write code, draft emails, summarize huge books in seconds. But here's the real puzzle we're unpacking today. How do we elevate these agents so they actually discover, verify, and defend top-tier scientific knowledge? I mean, it's one thing for an AI to sound like a scientist, but it's a whole different ballgame for it to actually be one. To really understand this shift, we first got to look at harness engineering. Think of this as the scaffolding around a building, or, the operating system for an AI agent. It's essentially the operational machinery, stuff like managing tools, memory, tests, and workflows. It's the gear that gives the raw AI brain the ability to step out and actually interact with its environment. Just look at the components here and how much operational reach this gives the AI. Harness engineering lets a coding model inspect your files, call an external tool, run a unit test, read the logs. It can even spin up little sub-agents to recover from basic errors. It literally transforms a simple chatbot into a system that can execute some pretty complex plans. But, here is the core problem we're facing right now: the illusion of competence. See, an operational system can be incredibly busy. It's calling tools, fetching files, doing all this stuff, while at the same time completely lacking true scientific novelty. It can spit out a flawless, paper-shaped output that tricks us into trusting it. But if you look underneath, there's absolutely zero real scientific discovery happening. So why does this happen? Well, it boils down to the ordinary agent workflow. The AI generates an answer, evaluates it against a benchmark, and repeats: generate, evaluate, repeat, over and over. This kind of shallow loop makes the system massively susceptible to reward hacking. It's just optimizing its language to beat a benchmark, rather than, making actual structural research progress. And that brings us to the central claim of this whole explainer: harness engineering versus the energetic paradigm. While harness engineering is busy asking how to make a model operate as a reliable working system, for true science, we desperately need a system that can discover, diagnose, test, and defend claims. We have to make the leap from just running operations to genuine research governance. Enter the energetic paradigm, or EP for short. Now, this isn't just some clever prompt trick or a minor add-on. No way. It is a complete scientific control layer placed directly over the operational harness. Think of EP as a super strict research governance architecture. It takes those ordinary wandering agent loops and transforms them into highly controlled, constraint-aware research trajectories. Under EP, we completely rethink what AI reasoning actually is. Borrowing a bit from physics, EP treats reasoning not just as spitting out text, but as the movement of energy. Think of it as research effort or focus moving through a problem space. Every problem has gradients, bottlenecks, strict constraints. So EP uses energy flow analysis and problem decomposition to make sure the AI moves this effort through valid deductive pathways. It's about achieving a breakthrough without wasting time on dead ends. Let's look at this direct comparison, because the shift in focus here is profound. On the left side, you've got the software engineering goal: how do we make agents work reliably? But on the right side, EP pushes us into true scientific governance. How do we make agents discover and verify knowledge reliably? It literally forces the AI to stop asking, okay, what tool should I call next? And start asking, wait, is this step actually reducing uncertainty? So, how does EP actually fix the pitfalls of the standard harness? Well, this architectural map shows how it fundamentally rewrites the way memory, self-improvement, and evaluation function. Standard agents get hopelessly lost in long context windows. They repeat failed routes, they hack benchmarks. But EP treats research as a tightly controlled state transition. It makes sure the AI isn't just spinning its wheels, but actually driving toward a mathematically valid conclusion. Take memory, for instance. Actually, this is super cool. Instead of just dumping a massive chronological log of actions into a context window, which, let's be honest, is like tossing papers into a messy filing cabinet, EP forces the system to classify its failures. It treats failures as blocked energy pathways and preserves them as negative evidence. Because its memory is structured by research function, the AI acts like a rat in a maze that actually remembers the dead ends. It literally never makes the same mistake twice. And EP also completely overhauls evaluation, separating local benchmark scores from real structural progress. See, a standard harness might let an AI basically hack a judge model just by writing more eloquently. EP stops this dead in its tracks by demanding strict, constraint-grounded scientific verification. Every single step has to be mathematically or logically verified against the actual rules of the problem. A high score is just one piece of evidence now. It's not the final truth. So what does this all mean for the final output? Well, it's a massive upgrade from fluent paper generation to rigorous claim governance. Before an EP system is ever allowed to draft a single word of a paper, it has to do the hard work. It must discover a true causal mechanism, design empirical tests, analyze its failures, and position its contribution to meet top-tier journal standards. It's no longer just hunting for random facts. It's deriving evidence that actually matters. Let's walk through this EP-controlled research loop. First, the AI identifies the structural constraints. Next, it discovers underlying mechanisms, and then it designs empirical evidence to test them. Crucially, and this is a big one, it preserves failures to reduce uncertainty. Only after doing all of that does it finally reconstruct the knowledge and defend its claim. It's literally a controlled, step-by-step enforcement of the scientific method. And this rigorous, multi-layered control is exactly why EP is already capable of guiding an AI from a vague, loose topic all the way to a paper-ready structure fit for elite scientific journals. You know, top journals don't just accept fashionable buzzwords, they demand mechanism-level contributions, they want anticipated counter-arguments, and heavily limited assumptions. EP bakes these exact uncompromising requirements right into the AI's core loop. I absolutely love this quote. Harness engineering supplies the machinery of action. EP supplies the discipline that decides which action matters. This distinction is everything. EP isn't here to replace the operational harness. It absorbs it. It takes mechanisms like file search and tool use and elevates them into a true research discipline. It acts as the governor, ensuring the machinery is actually building something real. So what's the ultimate takeaway here? Well, the future of AI isn't simply about scaling larger models with more parameters. Sure, scaling increases raw capability, but the decisive battle, the next great AI competition, is really over who can build controlled research intelligence. The true winner will be whoever builds a system that doesn't just operate, but genuinely governs the scientific process. Which leaves us with this final, kind of profound thought to ponder about the true nature of scientific discovery in the age of AI. If an AI can generate a flawless, beautiful paper, but it absolutely cannot govern its own reasoning, test its constraints, or learn from its blocked pathways, is it a scientist? Or is it just a machine that writes like one? Thanks so much for joining me on this explainer, and I'll see you next time.